I'm Charles Young, and I have an interesting electronics project. Recently, I acquired a number of Eberline ASP1 survey meters, which, with a speaker and 6 ranges, is a very capable and precise Geiger counter. You can see that the audio consists of the random clicks associated with Geiger counters. However, those of you that have watched my rock hounding videos know that I prefer to use tones to find my radioactive specimens in the field. So, what caught my eye about this meter is that it allows one to add just such functionality. There is a 16-pin header designed to accept a daughter board, and I will add an Adafruit Feather Sense microprocessor to optimize this meter for finding radioactive minerals in the field. For prototyping the daughter board, I will be engraving it on a CNC router. The model I am using is a Sain Smart Genmitsu 3018 prover. To keep things relatively simple, I will use a single-sided board. To make the engraving boards easier to solder, it is best to use wider pads and traces than is usual for boards sent off for fabrication. I will show you how to do this in Eagle. In the DRC Layers tab, you will select 2 layers, and we will ignore the top component layer as we go along. Here is also where you specify your copper and core thickness, which is what subsequent programs use to calculate engraving and drilling depths. On the Clearance tab, I specify a wire-to-wire and wire-to-pad clearance of 20 mil. On the Distance tab, I specify 40 mil. On the Sizes tab, I specify a minimum width of 40 mil. The effect of these relatively wide clearances is that it prevents wires from passing between pads, which is a potential source of solder bridges. To make the pads more robust for soldering, I substituted pin headers with larger pads and holes compared to normal IC sockets. To route the board, we select air wire in the selection filter and select all of the air wires. Then select the auto router. Make sure that the top layer has NA, the bottom is auto, and hit continue and start. With any luck, the first variant will be 100% complete. If not, you will need to rearrange components and/or use jumpers to simplify the routing. Hit End Job once you have selected one of the variants. Even though the board would work as is, a good practice is to add a ground plane. That is done by selecting the polygon tool and drawing around the periphery of the board. Be sure to have the blue bottom layer selected. I use a width of 10 mil and an isolate of 40 mil. After completing the polygon, give it the name of whatever you named your ground net, in my case, G and D. Under Tools, select Rat's Nest, and it will fill in the ground plane. Use Ctrl-S to save your work. Whether you are sending your board design out for fabrication or you are engraving it yourself, you will need to output Gerber files and drill files. To do this, select the Manufacturing tab. Since I'm going to engrave it myself, I select the bottom side and then click Cam. We don't need all the files like silkscreen or solder mask. Select bottom copper and export file. I stay in the project folder and press select folder. Say yes to replace any existing files and then OK. Repeat this process for the profile and the auto drill. This will result in the .gbr and .xln files being placed in the Gerber files and drill files folders. Flatcam is a free program that converts the Gerber and drill files to CNC files that contain the commands to operate the CNC router. In the process, the specific bits and tolerances are declared and various options can be chosen. Start a new project and open the .gbr and .xln files that we just created in Eagle. Since we will be engraving the bottom side of the PCB, we will need to flip the board around. Select Tool Two-Sided PCB. We will choose to flip it on the X-axis. Tap plus add and adjust the reference point to be exactly 1/2 of the X dimension. Tap the mirror button and adjust the X coordinate to keep the mirror origin at 0. Select the other two files and tap the mirror button for each. In the Project tab, double-click the copper bottom. This opens up the properties. Select Isolation Routing. We will be using a V engraver with a tool diameter of 0.1. I like to use 2 passes. Tap Generate Geometry and specify tool change at Z20 and NZ20. 20 millimeters is generally enough height to change a tool conveniently. I set the end move to 0,0 as well to bring the spindle back to the origin when the job is done. Tap Generate CNC Job Object, save CNC code, and navigate to the Gerber Files folder and save. We are going to repeat the process for the profile cutout. In the Project tab, double-click the profile. Select the cutout tool and the profile.gbr file. Specify the tool diameter of 2.0, cut Z of -1.8 because the board is 1.6 millimeters thick, multi-depth of 0.6, gaps none. Now generate geometry. Back on the Properties tab, generate CNC job and save CNC code. We repeat the process for the drilling file. On the Project tab, double-click the drill echelon. In the drilling tool, specify cut Z of -1.8 to cut through the 1.6 millimeter board. tool change of Z20, end move of Z1.0, and end move X and Y of 0, 0. Generate the CNC job object, save CNC code to the drill files folder. Now we are ready to move on to Candle. Candle is the program used with the Sain Smart CNC router to execute the CNC files that we just created in Flatcam. It is assumed that you have newly resurfaced your spoil board so that the PCB blank will lay perfectly flat. You will want to use double sticky tape to secure the PCB to the spoil board and then lightly clamp it. Do not use tight clamps as it will cause the blank to be of uneven height. The clamps also serve for electrical contact to the blank for height mapping. Mark the origin with a tape corner in case we need to realign the spindle after we start. Hook up the electrical circuit so the CNC router can detect the copper surface of the blank. Make sure the V engraver bit is sharp and fairly new or it will result in ragged cuts. Zero the Z-axis in preparation for height mapping. With the electrical circuit hooked up, I use the probe Z button of Candle. Open the copper bottom NC file to activate the mapping controls. Tap the Create button and set ZB to -0.3 to ensure that the tip of the probe reaches the board but does not go too deep by accident. Make sure that the border matches the dimensions of the board and that the grid is appropriate for an accurate mapping. Tap the probe button and observe the progress of the mapping. If the map has more than 0.5 millimeter difference in heights, you might consider adjusting a clamp or even resurfacing your spoil board. When the mapping finishes, use File Save As to store the map file. You will need to load this every time you load a new .nc file. I could not figure out how to close the mapping feature, so instead I just closed Candle, restart it, and open the copper bottom NC file. I also open the height map file and select Use Height Map. This adjusts all the commands to take into account the variances of height. We zero the spindle coordinates again. If after starting the engraving, the copper is not being cut deep enough, set Z0 a little deeper, perhaps by 0.02, and try again. You should see a slight trail of dust. Open the drill NC file and repeat the process above. I use a slightly smaller drill than specified to leave the pad as strong as possible. Measure the size of the largest pin. In my case, it is 0.66, so I will use a 0.75 drill instead of the specified 1.0 drill. open the profile NC and repeat the process yet again. I had a small problem with my profile.nc file in that it would pause for tool change at the beginning but would not resume. Since I had no reason to change tools, I just removed the following lines from the .nc file. After engraving, inspect the wires and pads under a microscope. Use a toothbrush or a fine tool to remove any burrs. Test all pads and lines for continuity to ground. This is great for prototyping and even a small number of production boards. For larger numbers, I recommend that you send the board out to a PCB fabrication house where solder masks and silk screen can be applied.